Okay, so we've done a lot of seeing how to calculate derivatives of functions when we can use the limit definition of derivative. So we take the limit of the difference quotients and we can figure out what the derivative is. But it's a bit tedious to do this every time you run across a new function. And there are common functions we run across all the time. It would be nice if we could figure out their derivatives, but we don't want to spend all day doing it. So what we'd like to do is have a way to just look at a function and very quickly say what its derivative is. And so with that in mind, our next goal is going to be to start developing some rules for calculating derivatives, which allow us to sort of bypass the limit definition. Those rules are based on using the limit definition, but the idea is that we do it once for a generic function, and then we're able to use the shortcut rule to quickly figure it out for all the other functions of that type. So the first type of function that we're going to look at are polynomial functions. And so we already know how to differentiate the simplest polynomials, which are constants and lines. We'd like to be able to generate things like differentiate things like x squared, x cubed, x to the 17th, and so on. So you can imagine doing something like x to the 17th using the definition of derivative could be very tedious. So let's try to see if we can come up with some better ways to do this. So the first thing that I'd like to introduce is the sum/difference rule for derivatives. This says that if f of x and g of x are differentiable functions, then the derivative of f of x plus or minus derivative of g of x, you can pick either sign you want, is equal to f prime of x plus or minus g prime of x. So whatever sign you picked over here, you have to pick the same sign over here. So I went through a proof of this in class. I think I'm going to skip the proof here, but it's maybe good practice to make sure that you know how to do this. It's in the textbook if you'd like to check. The second basic rule that we're going to need to know is the constant multiple rule, which says that if f of x is a differentiable function and c is some constant, then the derivative of c times f of x is equal to c times the derivative of f of x. In other words, you can pull the constant outside of the derivative and just differentiate the function on its own. So it's going to be useful to keep these two rules in mind. So the next rule that I'd like to introduce is the power rule. And this is the one that's going to do a lot of the work for differentiating polynomial functions. So this says that for any real number n, the derivative of x to the power n is equal to n times x to the n minus 1. So let me do a proof of this. Well, it's not really going to be a proof of this statement because proving it for any real number is a bit challenging, but I'll prove it for the case of n being a positive integer. So we can show using the binomial theorem or Pascal's triangle that x plus h to the power n is equal to x to the n plus n x to the n minus 1 times h plus some constant, which I'm going to call c2, x to the n minus 2 h squared. Then there's some more terms, and it goes all the way out to h to the power n. So this constant c2, I mean, all the other terms later would also have constants, like the next term would be c3 x to the n minus 3 times h cubed, and so on. And these constants are things we could figure out. So for example, if you recall Pascal's triangle, these things give the coefficients when you expand x plus something to the power n. So this would be n equals 0, n equals 1, n equals 2, n equals 3, n equals 4, and so on. So for example, if n was equal to 4, then our first coefficient is 1, our next coefficient is n, which is 4. Our next coefficient, c2, would be 6, then there would be 4 times x to the n minus 3, which would be 1 in that case, times h cubed, and then our coefficient of h to the power n is 1. And so similarly, you can keep making the triangle bigger. But what we'll see is that because we have an h squared here, eventually we're going to cancel some h's, and when we have an h squared, we'll still have an h left over. So when we take a limit as h goes to 0, whatever this constant is won't actually matter because the limit of this term will still be 0. The only term that will really matter is this one. So it is important to know what this first coefficient is. And if we look at our table, we see that the coefficients of that one go 2, 3, 4, 5, the next one will be 6, and so on. So the coefficient when we expand something to the power n is just n. So based on our knowledge of this, let's take a look at the definition of derivative. We have limit as h goes to 0 of x plus h to the power n minus x to the power n divided by h. And let's plug in our expansion here. So we'll have x to the n, but then minus x to the n. Those will cancel. We'll have an nx to the n minus 1 h plus c2 x to the n minus 2 h squared plus a bunch of terms with higher powers of h in them ending in h to the power n. Then we'll divide by h, and of course, as usual, I forgot limit as h goes to 0. Then you'll see that everything here has an h in it, so let's cancel the h from everything. And we'll get limit as h goes to 0 of nx to the n minus 1 plus c2 x to the n minus 2 times h plus some more terms ending in h to the n minus 1. And the point is that, again, there are some constants here which we could have figured out, but we didn't bother to. And they don't matter because we're taking a limit as h goes to 0, so all of these terms are just going to give 0. And the only one that matters is this first one, which we determined was nx to the n minus 1. So that shows why this is true if n is a positive integer. This can be generalized if n is a fraction or a negative number or an irrational number or something like that. But I am not going to go through the proof of that since it's just slightly more complicated. Okay, so let's see some examples. So what does this thing allow us to do? So let's suppose we have a function like f of x equals x to the power 19. It would be annoying to actually do this calculation with n equals 19. So let's not do that. Let's instead use the power rule. It says that if n is equal to 19, the derivative is 19x to the 19 minus 1, which is 18. So we can immediately say that the derivative is this, significantly less work. Let's suppose we have f of x equals square root of x. We can rewrite this as x to the power 1/2, and then we can apply the power rule to get that the derivative, in this case n is equal to 1/2, so we get 1/2 x, 1/2 minus 1 gives us a negative 1/2. So there's a problem at 0 because we would be dividing by 0 there, or also for negative numbers, right, because the square root is not defined there. But this formula is still valid as long as x is greater than 0. The function is just not differentiable if x is equal to 0. So next, let's try a different one. F of x equals 1 over x to the power 3. Well, this time we can rewrite this as x with a negative exponent. And so the derivative, again, use the power rule, n is equal to negative 3, so it'll be negative 3x to the negative 3 minus 1, which is negative 4. Or if you prefer, you could write this as negative 3 over x to the power 4. So as you can see, using the limit definition for all of these functions would have been extremely tedious, would have taken a lot more time and a lot more space than what I did here, so the power rule made our lives significantly easier. We can do more though, so remember we had the sum and constant multiple rules, so this allows us to differentiate polynomial functions. Remember, polynomials are sums of constants times integer powers of x. So we could have like 10x to the 7th plus 4x cubed minus 8x squared plus 17. And if you use the constant multiple rule and the sum rule, you can distribute this derivative to each of the individual terms and pull the constants out. And then you'll just be left with derivatives of x to some powers, for which we can use the power rule. So when you do that, if we just look at the first term, we'll have 10 times derivative of x to the 7th, which will give us 10 times 7 times x to the power 6. Then for this term, we'll get 4 times 3 times x squared. This term, we'll get negative 8 times 2 times x. And then this term, this is a constant, so its derivative is 0. And then if we just simplify this a bit, we see that it's 70x to the power 6 plus 12x squared minus 16x, and then plus 0. So that's it. So let's do one more example. Suppose that we have a function like f of x equals x to the power 90, and we want to find the 90th derivative of x, or of f of x. So in this case, of course, what we don't want to do is actually find 90 derivatives, but you'll see if you just start writing down a few that there's a nice pattern. So when we differentiate the first time, we get a 90 comes down out front, and then we'll get an x to the 90 minus 1, which is 89. So that's the first derivative. The second derivative is equal to, for 2 usually you just write prime prime. The second derivative is equal to 90 times 89 times x to the power 88. And hopefully you can see the pattern. We're going to accumulate a bunch of constants out front of the x that keep going down by 1, and the power in the exponent will keep decreasing by 1 each time. So if we differentiate 90 times, the power will go down to 0. So if we kept going, the 90th derivative, we'd have x to the power 0, so that would just be 1, and then we just get all these constants that we accumulated. So we get 90 times 89 times 88, all the way down to times 2 times 1. Another way of writing this is 90 factorial. And then if we had the 91st derivative, 90 factorial is a really huge number, but at the end of the day it's just a constant. So if we take one more derivative, we'll get 0. And this is one feature of polynomial functions, is that if you take enough derivatives, you'll eventually always end up at 0. So that's the power rule. It makes life a lot easier for calculating derivatives. I mean, now we can calculate derivatives of a lot more functions very quickly. And so in future lectures, we'll see more rules like this to help us very quickly find derivatives.